Today we're going to talk about two things. We're going to talk about a very special case where we can get an algebraic solution, which is if the net force on an object is constant, or at least one component of the net force on an object is constant. And then we're going to talk about situations in which we need to, about estimating interaction times. We're pretty good at estimating things like masses and even speeds, but times, especially short times, we're not so good at estimating. So we're going to talk about some techniques for doing that. So that's where we're getting today. So here we have a setup that, like, we played with this before. This is a cart with a fan on it. When I turn the fan on, it's like a little propeller, like those fan boats they use in swamps, actually. And I turn the fan on, the force that the air exerts on the cart is approximately constant. So it's pretty close to constant. So this is something we can use to experiment with a constant force on an object. And so here I turn the fan on. The air now exerts a force on the cart. It's obviously a force in that direction, and it's making its momentum increase that way. What this thing is a motion sensor. It works by emitting little ultrasound pulses, little pulses that are too high for us to hear. And they reflect off the cart. This is what this sail is for. It just makes a better reflector. And then there's a detector here. And by timing how long it took this pulse to travel, it can then calculate how far away the cart is from the sensor. And since it does this many times a second, if you get many of these points, it can actually take little differences and tell us how fast it's going in that direction. So we can get the x component of its velocity from the sensor. So what this will produce for us is some graphs that look like this, where this axis is time, and this axis is the x component of the object's velocity, and it's actually going to make another graph where this is the x component of its position. So we could write r sub x, or we could just write x for that. And what we're going to do is we're going to apply the momentum principle to predict what we think we're going to see in these graphs in different situations. And then I think you'll have a chance to do this in lab with similar equipment in coming weeks. So here we have a situation where, because this thing is clearly traveling much slower than 10 to the 8th meters per second, the x component of momentum is, to a very good approximation, gamma is 1, so it's 1 times m dx. And so x component of momentum, x component of velocity, you're going to get the same shape graph, just a different constant there. So let's just consider some things about what we think we ought to see in certain situations. So suppose what I do is I just push the cart in that direction for a short time and then let it go. So we're going to do this. So what do we think we're going to see in these graphs when I do that? So just suggest some things that these, let's concentrate on this. So v sub x or p sub x. What do you think that's going to look like? So it's going to be a line that starts out here, and then, okay, so I heard some people say it's going to be positive. I heard some people say it's going to slope down toward 0. Well, we're not assuming anything because this thing is going to measure it. So then the question is, what do you think we're really going to see? Okay, so nearly constant, but then why would it drop down to 0? Because it hits the end. Okay, so it should. So you're saying that it'll that it might look like that. What else are possibilities? Okay, so maybe it'll look like that. Could look like that. Okay, so let's see what we get. So this top graph here is the people who wrote the software were not very careful. So it says the top graph is velocity, but velocity is a vector, and a vector has 3 components, and that's not a graph of a vector. So it's really a graph of what? Could be speed, but speed is always a positive number, right? So this could be, is it speed? It's the x component. It's v sub x, isn't it? And this says position, but it's really x. And the origin is at the detector, and as usual, positive x-axis goes that way. Okay? So let's see what we get. Let's bring the cart back. And, wow, there's a magnet at the end. Okay. So I'm going to start the detector going. It makes little clicking sounds, but that actually is just to tell you it's on. So I'll start it going, and then I'll push it. Okay, so it wasn't quite what anybody predicted. You had some pieces of it. So it's a real world thing, right? It's not as idealized as a textbook picture would be. So what seems to happen here is we have this, so first of all, nothing's happening for a while. And then what happens here? We didn't have that piece of it in any of our graphs. That's the hand pushing it, isn't it? So it's definitely speeding up in the plus x direction. And that must be the time my hand was in contact with it. And let's see what this is seconds. So each square is a second. So it says my hand was in contact with it. It looks like it was nearly a second because it speeded up for nearly a second. And then it stopped speeding up. And so it's positive. The v sub x is positive. It's not as constant as we thought it might be, is it? So we saw it was, and then it sped up, and then there's a pretty significant downward slope, and then there was indeed a pretty abrupt decrease to 0, presumably when it hit the end. So it looks like the net. So what can we say about the net force on the cart during this interval? Was it 0? Well, there's no. Okay, so you have to be a little more precise in the way you say it. You're saying negative, and I think what you mean is it's in the negative x direction. There's a net force in the negative x direction. Is that what you mean? There's a negative x component because it's slowing down, isn't it? So its momentum, x component momentum is decreasing. That must mean all these f net delta t increments we're adding to it have a negative x component. And what do you think that's due to? Well, okay, so the cart's interacting with the air. Think it's anything else? Yeah. Yeah. So two important things, presumably, the air and the track, slowing it down. Okay. Let's try something a little more complicated. Okay. So I'll blank. We're not going to turn the sensor on first. We're just going to think about this. So I'll blank the screen so we don't get confused. Let's see what direction this force is in. Okay, good. All right, so we're going to start it here. I'm going to turn on the fan. Trying not to get my finger in the fan. And then we're going to let it go that way. I need to catch it before it hits the sensor. Okay, what do you think we're going to see? What is the graph of P sub x? I didn't blank the screen. Blank the screen. What is the graph of P sub x or V sub x going to look like here? So if I'm going to sketch it, where do I start here? Okay, so it starts at it's not moving, so it's 0. Okay, so we're predicting that it's going to start out at 0 until I release it. Then what happens? So the cart is traveling in the negative x direction. What does that tell us about the x component of momentum? Negative. Okay. So it's gonna keep going down. Is it gonna? Somebody said something like that. No. Okay, like this. Linear. Okay, it could be linear. And then what happens when I catch it? The cart stops, so what happens to the graph? It goes back to 0. So we all agree it's going to... Okay? So let's see what actually happens. So we'll clear this data. Delete last data run. Let's put the cart down here. And I'm going to have to start it and then walk around to the other end to turn the fan on. Okay. So it's not moving. I better stop the recorder. Okay, so the real world tends to be a little messy. What do you think happened here? I got my hand in the way of the detector, didn't I? So it was bouncing off my hand. I wasn't careful enough. But then I got my hand out of the way, and then V sub x was 0, and then, as you predicted, since it was going in the minus x direction, V sub x was negative, and because the speed was increasing, the magnitude of the velocity was increasing, the magnitude of the momentum was increasing, it got more and more negative until I caught it, and then there was a brief interaction. My hand must have been exerting a force on it to decrease the x component of its momentum, and then it went back to 0. Now, what can we tell about the force the air was exerting on the cart during this period? How do you know it was constant? Constant slope. So that's a pretty nice straight line. And we noted that we could rewrite the momentum principle in the form, we'll just write the x component, px final minus px initial over delta t, which is delta p sub x over delta t was f net x. So in fact, this is the slope of the momentum versus time graph, and that's the force. And if the slope is constant, the force is constant. Now notice that x versus t wasn't a straight line. Why is that? Here it's speeding up, so in 1 second here, well, it'll take half a second. Half a second here, it's going faster. So because the speed is increasing, and the displacement during the next time interval is more than it was in the previous time interval. And the speed gets even greater, so the next time interval, the displacement's even more. So we've got this, what looks like maybe a time squared dependence, and we'll see where that comes from. Okay, so other comments about this? All right. So one last thing. What are we going to see, do you think, if we do this? I turn on the fan, and I push it that way. What's it going to look like? Well, let's be more specific than a combination of the other two. Let's see if we can actually make a prediction of what we should see. Let's not worry about x versus t. Let's worry about v sub x versus t. We'll draw it bigger. Okay. So, what do you think? Okay, so a downward sloping line that crosses the axis. So you think it starts positive, and it goes. Okay, it's going to start at 0 and then curve up, and then straight line, and then go back to 0. That's a possibility. Other thoughts? Sorry, say again? So it could decrease more slowly. You mean it's not going to have that big a slope? Oh, so it's not going to be a straight line? So it's going to, what? Can you sort of like this? No, the other way. Oh, I see, the other way. Start out like that. Okay, so now think about the momentum principle. Think about what that might suggest to us. And let's see what we get. Okay. So we'll start the detector. I'll turn the fan on. And I'll give it a push. Okay, well, looks like we almost got it, but not as a detail. So it looks like from here to here, it looks like the slope is pretty straight. From here to here, it looks like the slope is pretty straight. It's just not quite the same. So it looks like what we got was close to this, when it got to this point, the slope is less. So it's kind of like that. So the fan, did the force direction of the force by the fan change? It didn't, did it? Magnitude probably didn't change either. So it looks like the track is level, pretty level, because, well, the initial momentum, what we mean by initial is just where we start. That's initial. Yeah? No, because my push, my hand loses contact with it here. This is the push, right? And remember that, so for that first time interval, all the little F net delta t's that I'm exerting get added up into the momentum, so that when my hand leaves, all the history of my push is now in that momentum at that time. So my hands are not acting on it anymore. Yeah, what do you think? Looks like it might, doesn't it? There's something about the friction force, huh? Yeah. Well, if the fan force, the fan force is always this way. Well, let's think through his suggestion for a minute. Okay, so the fan is always exerting a force in the minus x direction, right? When it's traveling this way, what's the direction of the friction force? Same way, right? When it's traveling this way, what's the direction of the friction force? Oh, maybe that way. So when it's going this way, there are two forces in this direction. When it's going back, there's a force this way and a force that way. And so the sum is somewhat different. The net force changed. So that's definitely a possible explanation. Now, what would you like to add to that, if anything? Oh, you're saying. Oh, so you're saying that you think the force exerted by the air depends on the speed of the cart, and it does. That's true. Air resistance does depend on speed, so that could be another factor. And we'd have to do some experiments with and without the sail to see. Yes, good point. Okay, so the punchline is, though, that we can tell a lot about the net force on a system by looking at the slope of the momentum versus time, or momentum v sub x versus time, p sub x versus time graphs, because if the slope is constant, then for some interval, that means the force is pretty constant. It's constant here too, it's just constant with a different value. So good job, and note that you can use this to reason about it, to make these predictions. And we'll be doing more of that.